Hey, this is Titans Math, and today we'll be going over Euler's formula, the components, performance, and application. Now, by definition, Euler's formula is a formula designed to determine whether a graph is planar or not. This can be determined with connected graphs, which are lines, vertices, and faces. Yet, what are those exactly?
Vertices are the dots that connect the edges in a graph. Typically, you can label these with letters as shown here. A graph can also be made of one single vertice. Edges are segments that connect the vertices making up the shape of the graph. Edges can be curved or straight. If you have more than one edge, they must be connected by a vertice. Faces are the empty areas in a graph created by intersecting edges. This graph specifically has 4 faces within the graph. However, when using Euler's formula, you also count the infinite face, which is the space outside the graph. So including the infinite face, this graph has 5 faces.
When you have a planar graph, you can reorient the vertices and edges so that no lines intersect like shown here. They're the same graphs, just moved around. Then we have non-planar graphs. These exist when a graph cannot be redrawn to have 0 intersecting lines. Some well-known non-planar graphs are the K5 on the left and utility graph on the left.
Additionally to 2D shapes, these are the 3D shapes that can be solved using Euler's formula. When these polyhedrons are projected, they form different shapes that have more easily counted lines, vertices, and faces. These are those projected shapes. The most recognizable one would be the cube. You are able to see how it was remodeled into a 2-dimensional plane.
Now let's get to the actual formula. Today we're going to be using the top form of the equation, although in the real world you can use either form. So today we'll be using V plus F equals E plus 2, also known as the number of vertices plus the number of faces equals the number of edges plus 2. Let's look at our first example. Here in this graph we have 6 vertices. 1, 2, 3, 4, 5, 6. And then with our faces, we have a total of 10, including that infinite face. And then when we count up all those edges, only the ones connected by vertices, we get a total of 11. Plugging that in, 6 vertices plus 10 faces equals 11 edges plus 2. 6 plus 10 equals 11 plus 2. And then when we add that together, we get a total of 16 equals 13. Since the two sides of the equation are not equal, this means that this graph is non-planar, meaning that this graph cannot be drawn without edges overlapping. Let's look at our next example. So, in this graph, we have 7 vertices. And then when we count up the faces, including that infinite face, there are 7. And then all of the edges equal to 12. So our equation is 7 vertices, 7 faces, equal to 12 edges plus 2. 7 plus 7 equals 12 plus 2. And then when we add that together, our equation is 14 equals 14. Since the two sides are equal, this means that this graph is planar, meaning that like shown in the picture, it can be drawn without the edges overlapping.
Why is this a reliable presentation, and why are we trustworthy presenters? Here we each presented to a person outside of this class and then gave them a problem to solve. In our experiment, 100% of students were able to answer the question correctly. This proves evidence that this video is a good learning or study tool for Euler's formula. These are our sources. We hope you enjoyed this presentation, and we hope we were able to provide you with a better understanding of this concept. Thank you.